Have you ever seen a news report about an election and just wondered, how? How can they possibly talk to 1,000 people and have any idea what an entire country is thinking? It feels, I don't know, almost like a magic trick, right? Well, today we're going to peek behind that curtain. We're diving into the powerful, but not so magical, tools that let us take a tiny, tiny little snapshot of a group and then make these incredibly confident claims about the whole shebang. And this isn't just about politics. This is the bedrock of how modern science works, how companies do market research, how factories make sure their products are up to snuff. So get ready. By the time we're done here, you'll get the logic that lets us go from a small, uncertain sample to something that looks a whole lot like certainty. No, really, let's just sit with that question for a second. Think about it. 1,000 people in a country of millions. That's like taking a single drop of water from the ocean and trying to figure out how salty the whole thing is. It just feels wrong, like it shouldn't work. But it does. And the bridge that connects that tiny sample to the entire nation, well, it's built out of some of the most beautiful and powerful ideas in all of mathematics. Today, we're going to walk across that bridge together. And you're not just going to see how it's done, you're going to get the keys to the toolkit yourself. All right, so here's our roadmap. First, we're going to talk about the difference between how statistics works in a textbook versus how it works in the messy real world. That's going to lead us right to our first major tool, something called the t-distribution, which is designed for that messiness. Then we'll shift gears and see how we can do something similar for proportions, percentages and polls. We'll even learn how to measure our confidence in the spread of the data, not just its average. After that, we'll cover a quick but important little adjustment for when you're sampling from a smaller group. And finally, we'll wrap it all up and put together your brand new statistical toolkit. Okay, so before we can really appreciate our new tools, we've got to understand the problem they were built to solve. So let's start off in this perfect, clean, ideal world of statistics, and then we'll see what happens when reality comes knocking. Okay, so in a first-year statistics class, you learn all about building confidence intervals with something called the z-statistic. It's beautiful, it's neat, and it works perfectly. But it relies on one massive, gigantic, totally unrealistic assumption that assumes that you already know the standard deviation of the entire population. That's what that little Greek letter sigma means. It's the true measure of how spread out all the data is. But just think about that. If we knew the standard deviation of the whole population, we'd probably also know the average, right? And if we knew that, why would we be taking a sample in the first place? It's a total catch-22. In the real world, out here where the data is messy, we almost never, ever know sigma. The only thing we have is the standard deviation from our own little sample, which we call S. And here's the problem. If you went out and took a different sample, you'd get a slightly different S. So our measurement of the spread has its own uncertainty built into it, on top of the uncertainty we have about the average. That is the real-world problem we need to fix. So, what do? We can't just pretend our little sample S is the same as the true population sigma. That's just wishful thinking. We need a new tool, a smarter tool, a more cautious tool, one that's designed specifically for this kind of incomplete data. And that brings us to the hero of our story today, the student's t-distribution. Here's a fun little piece of trivia for you. It was actually developed by a guy named William Seeley Gossett, who was working as a chemist for the Guinness Brewery in Dublin. He needed a way to monitor the quality of the stout with small samples. But Guinness had a policy against its employees publishing research, so he published his groundbreaking paper under the pseudonym Student, and the name stuck. So let's see what this brilliant student came up with. Now, look at these two formulas. At first glance, they look almost exactly the same, don't they? On the left, that's our z-statistic for the ideal world. On the right, the t-statistic for the real world. Let's break it down. The top part, the numerator, is identical. It's just the difference between our sample average, x bar, and the true population average, mu, which is the thing we're trying to figure out. But the bottom part, the denominator, that's where all the action is. In the z-statistic, we divide by sigma, the true population standard deviation, divided by the square root of our sample size, n. But in the t-statistic, we make one tiny, crucial substitution. We swap out that all-knowing sigma, which we don't have, for the humble s that we calculated from our sample. It looks like such a small change, just one letter. But making that change is like admitting, hey, I don't know everything. And the t-distribution is designed to respect that admission. It accounts for that extra bit of uncertainty, and that changes everything. So this is how we put that t-statistic to work to build our actual confidence interval. The overall structure is probably familiar. We start with our sample mean, x bar. That's our best single guess. Then we add and subtract a margin of error to create a range around it. Now that margin of error has two pieces. The first part is our old friend, the standard error, which is our sample standard deviation, S, divided by the square root of our sample size, n. The second piece is the new part, the t-value. This t-value does the same job the z-value used to do. It tells us how many standard errors wide we need to make our interval to achieve our desired confidence. But here's the key. For any given confidence level, the t-value is going to be a little bit bigger than the z-value would have been. And what does that do? It makes our margin of error bigger. It makes our final confidence interval wider. And why is that? It's our penalty. It's the price we pay for not knowing sigma. The t-distribution makes us be a little more cautious, a little more humble, by forcing us to create a wider, safer range. All right, let's really dig into the pieces here. We've got x bar, our sample average. We've got s, our sample standard deviation. We've got n, our sample size. Easy enough. But what about this t-value? How do we find it? Well, to look it up, we need two things: our confidence level, like 95%, and this new idea called degrees of freedom. For our purposes today, the formula is dead simple. It's just your sample size, n minus 1. But what on earth are degrees of freedom? Let me give you some intuition. Imagine I tell you to pick 3 numbers, any 3 numbers you want. But there's one rule. The average of those 3 numbers must be 10. Okay, so you pick the first number. Let's say you pick 7. No problem. You pick the second number, maybe a 12. Still no problem. But now, can you pick the third number? No, you have no choice. For the average to be 10, that third number has to be 11. The first 2 numbers were free to vary, but the last one was locked in. So in this case, we have 3 minus 1, or 2 degrees of freedom. This number tells the t-distribution how much solid information we have, and the more we have, the more confident it gets. This table right here, this shows the whole idea in action, and it's just so elegant. Now, for a 95% confidence interval, the classic z-value is always 1.96. It doesn't matter if your sample size is 10 or 10,000, it's always 1.96. But look at the t-distribution. With a tiny sample of 11, which gives us 10 degrees of freedom, the t-value is a much larger, much more cautious 2.228. It's forcing us to build a wider interval to account for our high uncertainty. But then, as we collect more data, say we get a sample of 31, giving us 30 degrees of freedom, look what happens. The t-value shrinks down to 2.042. It's getting closer and closer to 1.96. Why? Because with a bigger sample, our s is a much more reliable estimate of the true sigma. And if you could imagine having an infinitely large sample, well, at that point, your s would basically be sigma, and the t-value would become exactly 1.96, completely morphing into the z-distribution. So the t-distribution isn't just one curve, it's a whole family of them, starting out wide and cautious for small samples, and slowly getting sharper and more confident as our sample size grows.
Okay, theory is great, but let's make this real. Let's run through an example. Let's say we're a quality control engineer at a light bulb factory. We pull 25 bulbs off the line for testing. We find their average lifespan is 50 hours, and the sample standard deviation is 8 hours. We want to be 95% confident about the true average lifespan of all the bulbs we make. So, step 1, degrees of freedom. Simple. Sample size is 25, so we have 25 minus 1, which is 24 degrees of freedom. Step 2, find that critical t-value. We go to our t-table or use software. We look up 24 degrees of freedom and 95% confidence, and it spits out a value of 2.064. Step 3, now we build our margin of error. We take that t-value, 2.064, and multiply it by our standard error. That's our sample standard deviation, 8, divided by the square root of our sample size, 25. The square root of 25 is just 5. So we have 2.064 times 8 divided by 5, which works out to about 3.302. And finally, step 4, construct the interval. We take our sample mean, 50, and we add and subtract that margin of error. 50 minus 3.302 gives us 46.698, and 50 plus 3.302 gives us 53.302. So there's our answer. We can say with 95% confidence that the true average lifespan of all our light bulbs is somewhere between about 46.7 and 53.3 hours.
Awesome. So we've totally got a handle on how to estimate an average or a mean in the real world. But a lot of the data we care about isn't an average. It's a proportion. It's a percentage. What percentage of voters approve of a policy? What percentage of our products pass inspection? What percentage of the population is left-handed? Well, the great news is we can build confidence intervals for these things too, using a very, very similar logic.
Okay, so here is the formula for a confidence interval for a proportion. And wait a second, look closely. We're back to using z. What happened to the t-distribution? Did we just abandon it? Well, no. It turns out that for proportions, the underlying math works out a little differently. Thanks to a powerful idea called the central limit theorem, as long as our sample size is reasonably large, the distribution of all possible sample proportions behaves very, very much like a normal bell-shaped distribution. The common rule of thumb is as long as you have at least 10 successes and 10 failures in your sample, you're good to go. And because of that, we don't need the extra padding, the extra caution of the t-distribution. We can go right back to using our good old friend, the z-value.
Let's break this one down. It's actually pretty straightforward. First, we have p-hat. That little hat on top of the p just means it's an estimate from our sample. It's our best guess. So if we surveyed 100 people and 25 said yes, p-hat is simply 25 over 100, or 0.25. The second half of the formula is our margin of error. It's our z-value, again, usually 1.96 for 95% confidence, multiplied by that big square root thing. That square root is the standard error for proportion. Inside it, we have p-hat times 1 minus p-hat, all divided by our sample size, n. That term is what gives us a measure of how much we'd expect our sample proportion to bounce around if we were to take many different samples.
Let's run the numbers with that left-hander example. Step 1, the data. We talked to 100 people, n is 100. 25 of them are left-handed, so our p-hat is 0.25. We want 95% confidence. Step 2, the z-value. For 95% confidence, it's our old friend, 1.96. Step 3, now we just plug and chug. We take our p-hat, 0.25, plus or minus 1.96, times the square root of, okay, let's see, 0.25 times 1 minus 0.25, which is 0.75, divided by our sample size of 100. Step 4, the result. You run that calculation and the margin of error comes out to be about 0.085. So we take our 0.25, or 25%, and we add and subtract 8.5%. That gives us a final confidence interval that stretches from 16.5% all the way up to 33.5%.
Now, this is maybe one of the most important parts of this whole explainer, because it's so easy to get the interpretation wrong. It is so tempting to say there's a 95% chance the true answer is between 16.5% and 33.5%. But technically, that's not correct. Think about it. The true percentage of left-handers in the world is some fixed unknown number. It is what it is. It's either inside our specific interval or it's not. The 95% isn't about the answer, it's about our method. What it really means is this. If we were to do this whole experiment over and over and over, get a new sample of 100 people, calculate a new interval, and do that thousands of times, we would expect that 95% of the intervals we created would successfully capture or contain the true population proportion. Our confidence is in the reliability of the process itself.
Okay, we've got means, we've got proportions, we're doing great. But sometimes the average isn't even the most interesting thing about a set of data. Let's go back to our engineer in the factory. This time she's making pistons for a car engine. Now, it's great if the average size of the pistons is perfect, but if some are way too big and some are way too small, the engines are still going to fail. What she really cares about is the consistency, the spread, the variance. And believe it or not, we have a statistical tool for building a confidence interval for variance too. But for this job, we need to call in a new specialist distribution.
To build a confidence interval for the population variance, which is just the standard deviation squared, we use something called the chi-square distribution. It's represented by that Greek letter chi, which kind of looks like a fancy cursive X. And you can see right away, this formula is a whole different animal. It is not our simple, symmetric, best guess plus or minus a margin of error. Because the chi-square distribution itself is not symmetric, we actually have to calculate the low end and the high end of our interval with two separate calculations.
And this is why the formula looks so weird. Unlike those nice, symmetric, bell-shaped curves for z and t, the chi-square distribution is lopsided. It's skewed. It can't be less than 0, because variance can't be negative, so it's all bunched up on the left and has this long tail stretching out to the right. Because of this shape, we can't just find one critical value. We have to find two different ones. A chi-square value that cuts off a little bit of area in the right tail, and another one that cuts off the same amount of area in the left tail. Now look back at that formula. The top part of the fraction, the numerator, is the same for both sides. It's your degrees of freedom, n-1, times our sample variance, s squared. But to get the two ends of our interval, we divide that same number by our two different chi-squared values. And here's the part that can feel a little backwards at first. To get the lower bound of our confidence interval, we divide by the bigger chi-squared value from the right tail. And to get the upper bound, we divide by the smaller chi-squared value from the left tail. It's a little mathematical inversion, but it's what makes the interval work for this skewed distribution.
All right, we are on the home stretch. Just one last adjustment to add to our toolkit. Up to this point, all of our formulas has basically assumed we're sampling from an infinitely large, or at least a massively large population. Think pulling all of the United States. But what if you're not? What if your population is a factory with 500 workers and you survey 100 of them? Or a single high school with 1,000 students and you sample 200? What happens when your sample isn't just a drop in the bucket, but a pretty significant chunk of the whole thing?
For these situations, we need to use a little tweak called the finite population correction factor, or FPC, and you only need it when two conditions are met. First, you have to be sampling without replacement, which just means you don't put a person back into the pool to be chosen again after you've already talked to them. This is how pretty much all real-world sampling is done. Second, and this is the key, your sample size, little n, has to be more than 5% of your total population size, big N. So if you're polling the entire country, your sample of 1,000 is a tiny fraction of a percent. You don't need this. But if you're polling 100 workers at a 200-person company, well, your sample is 50% of the population. You absolutely need to use this correction.
And this is the correction factor itself. You calculate this number, the square root of the population size n minus the sample size n, divided by n minus 1. And you simply multiply it by the standard error part of your confidence interval formula. Now just look at that fraction inside the square root. The top is always going to be smaller than the bottom, which means this factor is always going to be a number less than 1. So what does that do? It makes your standard error smaller, which makes your margin of error smaller, which makes your final confidence interval narrower. And that should make perfect sense. If you have a population of 100 people and you take the time to sample 99 of them, you know almost everything about that population, don't you? You have very little uncertainty left, so your confidence interval should be super, super narrow. The FPC is just the bit of math that makes that happen.
And there you have it. We've done it. We have assembled a complete, powerful, and practical statistical toolkit. We started with this one simple, nagging problem: what do we do when we don't know the population's standard deviation? And from there, we built out a whole system for handling means, proportions, even variance. And we've learned how to fine-tune it for special cases.
Think of this slide as your cheat sheet. It's your guide for picking the right tool for the job. It all starts with one question. What is it that you're trying to estimate? If your goal is to estimate a population mean and average, you then have to ask yourself, do I know sigma? If you're in that rare textbook situation where you do, you use the z-distribution. But for the other 99.9% of the time, when you don't know sigma, you grab your trusty t-distribution. Now, if your goal is to estimate a population proportion, a percentage, as long as your sample is big enough, you can go ahead and use the z-distribution. And finally, if what you're really interested in is the spread, the consistency, the population variance, then you need to pull out that special lopsided tool, the chi-square distribution. This right here, this is the decision-making process that goes on inside a statistician's head every single day.
So the next time you see a poll in the news that says 47% of people approve with a margin of error of plus or minus 3%, you won't just see the numbers. You'll see the invisible confidence interval around that 47%. You'll understand the beautiful logic that allowed those researchers to talk to a small group of people and make a powerful, reasoned, confident statement about a much, much larger world. We've journeyed from a simple question all the way to a full toolkit. You now have the intellectual equipment to not just consume data, but to understand its limits, to measure its uncertainty. So the only real question left is, what part of your world are you going to measure first?